Alo, alo.
Thầy là chuyên gia mở cửa bên đấy, xong rồi nó chói cha chỗ em buồn lắm.
Vẫn hơi vắng nhỉ, người ta bắt đầu nhé. Và nào đóng một cái cửa đi. Hơi lạnh một tí nhỉ. Các bạn biết chỉnh nhiệt độ ở đâu không?
Tôi vào điều hòa lạnh thế. Tôi vào điều hòa lạnh phải.
Alo. Okay, we start. I see that half of you are still sleeping. No, I mean the people who are not here. People who are not here, they are still sleeping. Not you. Because anyway, I will wake you up. Okay, we started last time the kinetic theory of gases. We know that the kinetic theory of gases based on the assumption that the gas is an ideal gas. I think now you are able to distinguish between the ideal gas and the real gas, right? The ideal gas and the real gas. So in the ideal gas, particles are supposed to have no volume. And the collisions between particles are elastic. So we know elastic collision already. And there's no interactions between particles except during the collision. Good. And we also know now the ideal gas law could be written as PV equal nRT. So P is the absolute pressure and is the number of moles of the gas. T is the temperature, okay, measured in kelvins. And R is the ideal gas constant. When we say constant, it doesn't mean that it has only one numerical value. You already understand why. Because in physics, we have to pay attention on the unit. Can someone close the door, please? Bạn nào vào sau đã vào muộn thì chú ý nhé. Cửa cứ để mở toang ra vậy. Okay, the unit, please remember very well. We have always pay attention on the unit. Here, the two most important numerical values that you often use is this one. Okay, when the volume is measured in liter, the pressure is measured in atmosphere. Of course, the mole and the temperature. And this value. So here we convert things to joule per mole Kelvin. Good. So we also calculated the work done by an ideal gas at constant temperature, at constant volume, and at constant pressure. What is the work done by an ideal gas at constant temperature? At constant temperature, what do we have? At constant temperature, what do we have for the work done by an ideal gas? thanh niên người ta chat chít này tập trung đi vào lớp rồi đấy. Riêng cậu này về đi ạ. Về. Đi về. Tôi đã bảo vào lớp rồi, tôi đã bảo tập trung rồi. Đi tới tận nơi đây rồi vẫn còn chơi điện tử. Tập trung được chưa ạ? Okay. So remember, this is the expression to calculate the work done by an ideal gas at constant temperature. Even you do not remember it, you can re-establish it from the beginning. Okay? We know that this is an ideal gas, we apply the ideal gas law, and we know the work done by a gas can always, I say always, be calculated using this expression. Okay? So you can always apply it to find the three cases of the work done by an ideal gas: at constant temperature, at constant volume, and at constant pressure. Okay? So remember, okay, another name. Constant pressure, we also say isobaric. Constant volume, we say isochoric. Okay? Constant pressure, we say isothermal. Remember the word I mean. Yeah, isochoric, isobaric, and isothermal. So, because last year, some people cannot even recognize this word, not talking about the way to solve the question. They have to overcome first the barrier of the language. So this one we did it, this one we did it. You know how to apply the ideal gas law, right? You know how to calculate the work done by the gas. Then we also verify, we develop together the expression that relates the temperature and the speed of the molecule. Okay? The speed of the molecule. So we did it. After a long way to go, we go to this expression. Okay? And we define also the root mean square speed of the molecule. And I think we somewhere stop here. Did you see it? Already, right?
Yes.
Okay. This one?
No,
Not yet? Good. So, I recall what we have seen together last time. Now we continue. We go to another definition of the mean free path. Here I have my gas molecules, and we know that for the gas molecules, they are moving in any direction, right? With different speed. Vào lớp rồi ạ. Để ngủ đi. Dậy rửa mặt đi. Tất cả những bạn nào chưa rửa mặt đi. Hãy rửa mặt xong rồi ngủ lại ạ. Okay, here I have my gas molecules. So if I consider this one, for example, Yeah, please follow me. So it will move in any direction. So it will collide with all the molecules for sure, right? So it can move to here to collide this one, to here to collide this one, or it can move further to go even here, you see, to collide with this one. So then, here it will do a distance. From here to here it will do a different distance. Okay, here also we have a different distance. Then what will be the average distance? Average distance that this molecule can perform before colliding with all the molecules. With all the molecules. So we call it the mean free path. So mean free path is actually the average distance traversed by a molecule between collisions, right? This molecule can go in any direction and perform different displacements. Then what will be the average distance that this molecule can travel before colliding with all the molecules? And we can establish the expression of the mean free path, what we call lambda here. We can establish the expression for it. So we based on the assumption that of course we know that the correlation is elastic, and we based on the assumption that the molecules moves in the straight lines. Okay, moves in the straight line. A constant speed also. A constant speed. So then we can try to establish a relationship, an expression for the mean free path. So here I have a model of one molecule. One molecule. And here this is the situation when my molecule collides with other molecule. So the two molecules will get into contact to each other. My molecule will have a mass m and a diameter t. Okay? So when it gets into contact, we will have a diameter here of 2d. Good. That's why we can replace this model to simplify things. We can replace this model with this model of only one big molecule having a diameter of 2d. Okay? And the mass m. Good? Do you understand until here? So I replace this model by this model to simplify the question. Yeah. And in this case, we consider that only one molecule is moving and others are at rest. Yeah. For now, we consider it. And after that, we will return. We will consider that all molecules are moving. But for now, to simplify things, we consider that all the molecules are at rest. Good? So we consider only the problem of one sphere molecule which is moving. Easy, right? Here I already explained that we replace this one by this one. So I call here delta t the time, okay? The time between collisions. So the time that my molecule can travel before colliding with other things. And here, this is the model. The length that my molecule performs during collisions, between collisions, is actually V delta t. You agree with me? The distance is the time times the speed. Then we have this. So this is the length that my molecule can travel. Can travel between collisions. And the volume that my molecule can sweep out is actually this cylinder, right? You agree with me? Because my molecule has a diameter of 2d and it will travel at a speed v during the time delta t. So it will sweep out a volume of this cylinder. Good? You understand until here? So the number of collisions that occur in the time delta t should be equal to the number of molecules that lie within this cylinder. Of course, all the molecules should be included inside of this cylinder for the collisions to happen. That's why here we say that the number of collisions that occur in time delta t should be equal to the number of molecules that lie within this cylinder. So here we already consider that all the molecules is represented by a point only. Okay? Then we are able to calculate the number of molecules in the cylinder. Yeah, we are able to calculate it. Chỗ gì đấy ạ? Vấn đề đấy là gì? Em tắt đi cho đây. Em đùa tôi à? The number of molecules in this cylinder is actually the number of molecules per unit volume times the volume. You agree with me? Of course. What I do is just calculate the number of molecules per unit volume and we times the volume. So the number of molecules per unit volume is actually N over V, right? V is the volume and it's the number of molecules. Is it okay? And here, this is the volume of my cylinder. Easy, right? Until here you still follow me. If I say, okay, here the mean free path, what I call, is actually the length of path during delta t over the number of collisions in delta t. Good, because I want to find the average free path. So lambda is the length of path during delta t over the number of collisions in delta t. Then, what do I have? What do I have? Here, I will replace, okay, this is the length of path that my molecule can travel during the time of delta t. Here, this is the number of collisions in delta t we just established. When we simplify it, what do we have? We have this expression. Okay? When we simplify it, we have this expression. But here, remember, this expression is based on the assumption. Remember the assumption that we just mentioned is that only our molecule is moving while others are at rest. But in reality, all the molecules are moving. In reality, all the molecules are moving. Then what will be changed? What will be changed? So here, you see here, okay, I put it, okay. You see here, we have a speed. Here, we have a different speed. Okay? We can cancel it out only when we consider one molecule is moving. But if we consider that all molecules are moving, I mean, my molecule, the thing I'm considering, is moving, others are also moving, then I cannot use the speed that I see. We have to consider the relative speeds between molecules. Okay, am I right? So you just study the mechanics. So you see that, okay, one molecule is moving in this direction. The others is moving in other direction. Then the real speed between molecules should be calculated using the relative speed, right? Then here, what we have in the numerator is actually the average speed of the molecules relative to the container, while the speed in the denominator is actually the average speed of our molecule relative to the other molecules which are moving. So you see here the problem. Other molecules, they are moving. So we have to replace, in the case of all molecules are moving, we have to replace this speed by the relative speeds between molecules. How to do so? Right? So in mathematics, I recall a little bit of mathematics. If we have two molecules like this, random molecular velocities, they have random molecular velocities. So V1 and V2. So the relative speed can be written like this one. Okay, step by step. Then for the value, we can denote it, and it becomes this formula. Này các bạn học toán vector chưa nhỉ?
Rồi ạ.
Rồi đúng không? Các bạn chú ý là tích vô hướng của hai thằng thì bằng không đúng không? Good. Cho nên là vì sao mà nó thành thằng này? Ok, học rồi thì tốt. Good. So we have the relative speed between two molecules who are moving. We have this expression. Now we replace this expression. Yeah. Yeah. We replace this expression. We know that in our case we consider that the speed is constant, okay? Speed is constant during the movement. Các bạn chú ý nhé, lúc nãy là ta đã nói là cái vận tốc của cái phân tử của chúng ta khi chuyển động nó là không đổi đấy. Cho nên là vì sao tôi để V1 và V2 ở đây đã? Tôi đang consider là tất cả các cái phân tử nó chuyển động ở một cái speed bằng nhau. Okay, so here I have this expression at the end. So this is the relative velocity between two molecules who are moving. Then I replace in my formula. Okay, this time I replace the speed here in the denominator by my relative speeds, and I simplify again. You will see there's a difference. Okay, there's a difference of the root of 2 here in the denominator. Good. So this is the expression. This is the expression of the mean free path. Here, this is the expression of the mean free path. I give you an example of the air molecules, the difference of the mean free path of the air molecules. So at the sea level, I mean in our level, the mean free path lambda of the air molecules is around 0.1 millimeters. But when we go to the height of 100 kilometers, we see that the lambda now becomes 16 centimeters. It means that the density of the air, you know the density of the air when we go high, is much lower. So the chance for one molecule to go to another molecules and collide with other molecules is smaller, and the average distance that one molecule has to travel to be able to collide with other molecule is 16 centimeters. When we go to the height of 300 kilometers, our lambda becomes 20 kilometers. So one molecule has to travel 20 kilometers to be able to meet all the molecules. So you see the difference. Good. Here I have an exercise. Please try to do it in 5 minutes. Here we have to calculate lambda, the mean free path for oxygen molecules, okay, at 300 Kelvin and pressure of 1 atmosphere. We assume that the molecular diameter of oxygen is 290 picometer, and our gas is an ideal gas. This is the question A. The question B, now we know the speed, okay? We know the speed of our oxygen molecules, 450 meters per second. Then what is the average time T between successive collisions for any given molecule? Try to do it. How many people can do it? Do you have the results? Can you try to raise your hand? How many people can do it? Bạn nào làm được ạ? Các bạn giơ tay thử xem, tôi muốn xem bao nhiêu phần trăm lớp mình làm được bài khá là đơn giản như thế này.
Ai làm được giơ tay ạ?
Ai làm được giơ tay để xem ạ? Không ai làm được ạ? Okay. Here I give you the solution. Okay. We based first on the expression of the mean free path, and we combine with the ideal gas law. We should be able to find the mean free path. Good. Okay, here we replace by using the ideal gas law. Is it okay? Second question is very easy. But for the first one, we start from the expression of the mean free path. So we have this one. We need the number of molecules per unit volume. We can use the ideal gas law to find the expression. What is K here? Chữ K ở đây là cái đại lượng gì đấy ạ? Chết rồi, tất cả những ông mà đang ngơ hết mặt ra là hỏng đấy. Boltzmann constant, right? Boltzmann constant. What is the value of Boltzmann constant? Good. Is it easy? Easy, right? So we continue this part before we take a break. Or do you like that we take a break now? Okay, let's take a break and then we come back in 10 minutes at 6.
Ở đây có một cái lambda ở đây cái câu B
Chương này còn nhiều nội dung lắm nữa này mà chưa biết làm sao mà để đi kịp được. Cái này là tối nay là còn trận gì các em nhỉ? À, Hồ Thụy Sĩ. Đây là này khó ngủ phết nhỉ. Xong rồi ngày mai là nghỉ à? Hay như thế nào? Hả? Nghỉ đá ấy, tôi không nói nghỉ học. Đúng không? Hết hôm nay xong rồi tới ngày mai thì còn trận nào không hay là nghỉ? Nghỉ hả? Nghỉ ngày kia đá tiếp à? Thứ sáu à? Ok, đấy còn thở được mấy ngày. Thật là tuyệt vời các em ạ. Bây giờ tôi mới biết là máy tính của các em nó có ghi nhớ tất cả các hằng số vật lý. Thế thì ok, cảm ơn thông tin hữu ích. Bởi vì tôi sẽ loại bỏ tất cả những cái câu mà tôi đề nghị các em là nhớ hằng số vật lý các thứ là bao nhiêu, năm ngoái năm kia tôi vẫn đưa. hỏi là Boltzmann constant nó là bao nhiêu, đơn vị là gì. Hoặc là ideal gas. Ok, cảm ơn các em, thông tin rất là hữu ích.
Em không biết cái đấy tồn tại. Cái đấy tồn tại á?
Bản thân mình cũng học hỏi thêm.
Em không biết cái đấy tồn tại cơ. Chỗ nào ấy thầy? Chỗ nào ấy thầy?
Very good. It's good to study with you, huh? So I think we have to continue. We have still a lot of contents to discuss together in this chapter. So this chapter is a little bit hard for you. Anyway, this is physics at the university. This is not physics at high school anymore. So, please, we are back to the lesson. Please, if you are chatting, surfing Facebook, please stop. Yeah, stop Facebook. No more Facebook. We continue. Good. Được chưa ạ? Tập trung lại được chưa ạ?
Thầy Văn chưa hiểu. Đừng nói rồi đâu.
Mày thế không thì lại thành cho điểm. So we now the right thing is that you stay focused here. Okay? You stay focused here, so you will not be afraid of the exams. Any questions in the exam? We already examined together. We already discussed together. So nothing to be afraid of.
Nghe cái giọng này em bị sợ.
Đấy là lý thuyết ạ. We continue on.
Tất cả chỉ là lý thuyết thôi.
So now we go to the distribution of molecular speeds. Here, this part I will go very quick because it's anyway very hard to remember also. The question is that, okay, we know that we can calculate the average speed of the molecule. So we can use the root mean square value. But for example, now we want to know, for example, how many percent of the molecules will have the speeds greater than the average value, the root mean square value, for example. How many percent will have a speed lower than that? Right? Then, to answer this question, Maxwell, he solved it during the 19th century, not us. And he solved the problem of finding the speed distribution of the gas molecule. And he proposed this function. Okay, here, this is the Maxwell speed distribution law. I will not ask you to redevelop this formula because this is too complicated. This is even complicated for you to remember already. So the probability distribution function, this is what we call PV. Yeah, P is the probability. Yeah. You know, it's the molar mass, T temperature, V is the molecular speed, and R is the gas constant. This is what we call the Maxwell's distribution law. So based on this one, we can calculate the probability of some molecule, of a certain molecule having a speed that is maybe greater than average speed. Here, please look at this figure. Here, I have PVDV, which represent this area, right? PVDV. So actually, now you know that the differential speed is actually a very small change in the speed. We have the whole distribution of the speed is like that. Here, this may be the maximum speed. Okay, the maximum speed. Here, this might be the minimum speed. So, in our gas, there are speeds that will have the maximum speed. There are molecules that will have root mean square speed, and so on, because we have different kinds of speeds. And the distribution here, this is to say that the probability of one molecule to be found in this area, or this area, or this area, and so on. The sum of the area here, this area is equal to 1, because we are talking about the percentage. So the sum here is equal to 1. Then if you want to find the fractions of molecules with speeds in an interval, let's say from V1 here to V2 here, we can use this formula. Okay? For example, if I want to calculate the fraction of molecules with speed within, for example, 580 meter per second to 680 per second, then I will replace 580 here, 600 here, and I use the formula, this one. This one. So I replace this very easy to remember expression. Okay, very easy to remember expression to this integral. Then I am able to determine the fractions of molecules with speed in this interval. Được chưa? Bây giờ các bạn muốn xác định cái phần mà các cái phân tử nó chuyển động ở cái vận tốc trong cái khoảng vận tốc từ V1 đến V2, thì các bạn rất đơn giản, các bạn thay cái công thức rất là dễ nhớ của Maxwell vào cái biểu thức này, vào cái interval này, và các bạn giải cái biểu thức đó một cách rất là dễ dàng. Chúng ta có bài này mà cho kiểm tra thì tuyệt vời đấy, tính trong vòng 2 phút. Dễ đúng không ạ? Số nếu dễ thì tôi cho vào nhé, thay bằng mấy cái câu
dễ với thầy.
Like I said, the root mean square speed is only one kind of average speed. We can also determine, here I do not develop anymore, I give you the expression directly. But the average speed of the molecule, the average speed of the molecule can be calculated using this formula. Okay. So you see sometimes the average speed is very different than the root mean square speed because there are two ways to calculate it. So this is the expression to calculate the average speed. The expression to calculate the root mean square speed we learned already, and this is the expression to calculate the most probable speed. I mean here, the speed that can be found here, it corresponds to the speed that happens the most, in the gas molecules. Good? In the gas molecules. For example, here we have, 1,000 gas molecules here, but the number of gas molecules having the speed of 400 meters per second, we take the biggest part, then we call it the most probable speed. Cái vận tốc mà các cái phân tử khí nó có được, nó xảy ra được nhiều nhất thì người ta gọi là cái most probable speed. Được chưa? Most probable speed. Here we have the average speed, here we have the root mean square speed, and here we have the most probable speed. Good. Do you have time to note?
Yes.
Okay. If you have time to note, we try to do this one very quickly. Actually, last year I simplified the part of speed distribution in the exam because it's quite complicated to remember. So don't worry about it. We have to learn to know. To know that okay, there's a way to calculate the speed distribution of the molecules. It doesn't mean that I will force you to remember it and give it in the exam. But we have to learn anyway, okay? We have to learn to know that there's a way to calculate it. It is also an important part of the kinetic theory of gases. We do not have it in the exam, but we have it in the tutorial part. When we consider the gas molecule distribution. Cái phần này các bạn không có ở trong kiểm tra, nhưng mà nếu bạn nào học practical physics ấy, thì tôi có bài thực hành liên quan đến cái phần này. Ok nhé. So try to calculate it and do not forget the units. If you forget the units, you will have different speed, different results. So you see, if we calculate it wrong, we will see the three different values. Okay, the three different values. For example, for a gas, oxygen gas molecules, at the room temperature of 300 kelvins, this gas will have an average speed of 445 meters per second, a root mean square speed of 483 meters per second, and a most probable speed of only 395 meters per second. Okay, we continue. Now, this is a very important part in the exam. For sure, you will have it during the final exam. Now we go back to the problem of specific heats, and we consider the specific heats of an ideal gas. Last session, during the first session, I already told you that we have to distinguish between the specific heat at constant volume and specific heat at constant pressure, if you still remember. Because for the gas, the two values are very different. Okay, Cp and Cv. So we call it Cp, the specific heat at constant pressure, and specific heat at constant volume for a gas substance. These two values are very different. Now, let's say we consider a monatomic ideal gas. We consider a monatomic ideal gas. So, monatomic ideal gas, these are gases having individual atoms, rather than molecules. For example, helium, for example, argon. For diatomic gas, they will have two molecules, right? For example, nitrogen, we call it diatomic gas. We may have polyatomic gas, for example, methane, CH4, it will contain more molecules, right? More atoms in one gas molecule. Here, for example, helium or argon, we have only individual atoms. That's why we call it monatomic gas. So remember the word monatomic gas, diatomic gas, polyatomic gas. Then we assume that the internal energy of the monatomic gas is actually the sum of the translation of kinetic energies of the atom. Okay? The internal energy is actually the sum of the translation of kinetic energies of the atoms. Actually, in reality, we might have the rotational kinetic energy. Actually, the translation of kinetic energy is the change energy when the molecule is moving in a straight line like this. That's why we say translation of kinetic energy. Okay? But there's, for example, if this atom rotates in itself, normally it also contains energy to be able to do that. But here, in the quantum theory, it disallows the rotational kinetic energy for individual atoms. Một cái phân tử nó có thể chuyển động thẳng và đó là một cái cách nó mang năng lượng ạ. Cho nên vì sao ta có cái chữ translational ấy, để chỉ là từ hẳn đấy, translational kinetic energy. Nó còn có các cái chuyển động quay nữa, có thể là quay quanh chính nó đấy, quay quanh trục chính nó đấy. Nó cũng là một cách khác để nó store energy, một cách khác để nó store energy. Tuy nhiên là trong cái quantum theory ấy, thì với các cái monatomic gas này thì họ coi là nó không được mang năng lượng, nó không có năng lượng. Cho nên vì sao ta mới có cái assumption là cái internal energy ở đây nó chỉ là tổng của các cái translational kinetic energy, có nghĩa là đối với for monatomic ideal gas there's only one way for the gas to store energy is by the translation of kinetic energy. Okay? It's by the translation of kinetic energy. You will see later on for the polyatomic gas, for example, it can store also energy by the rotational kinetic energy. Not only the translational kinetic energy, but for the monatomic gas, there's only one way for the gases to store energy. This is by the kinetic, translational kinetic energy. So, this one we know, right? The average translational kinetic energy of a single atom can be calculated using this one, and it should be equal to the internal energy of that atom. For n more, okay, so we have this number of molecules, this number of atoms, then we should be able to rewrite, for n moles, then the internal energy of n moles of the ideal gas can be written in this formula. Okay? And remember, if we replace this ratio with the Boltzmann constant, what do we have? Right? We should be able to have this one. So here K we replace with this ratio, and A is gone. There's only R here. Then for a monatomic ideal gas, we have this one. The internal energy should be expressed in this way. See that again? Please remember this very well. Here we see once again the internal energy depends only on the temperature. Yeah. The internal energy of the system depends only on the temperature. For that reason, we can increase the internal energy of our gas by increasing the temperature. Yeah. And only the temperature we decide it. Now, let's go deeper into the problem of CV and CP. CV and CP. Here we consider n moles of an ideal gas, okay, at a certain pressure here and certain temperature. Yeah. Good. In a fixed volume. Now, if we raise the temperature by an amount of delta T while keeping the same volume, then what will happen is that the pressure will also change to an amount of delta P. Okay? We can calculate the heat Q. Yeah. That relates with this change. Do you remember how to calculate it? The heat is actually N C delta T. Okay? We call it CV because we have constant volume. So Q equal N CV delta T. Yeah, with CV, the molar specific heat at constant volume. Molar specific heat at constant volume. I try to do it slowly. The molar specific heat at constant volume. So the amount of heat needed to raise 1 mole of a substance by 1 Kelvin or 1 degree Celsius, we call it CV. At constant volume, we call it CV, and Q equal N CV delta T. Okay, clear until here? If we substitute this expression in the first law, what do we have? Remember the first law? Còn nhớ first law mà. Here we should have the change in internal energy equal heat, right? Now we replace the expression of heat and CV delta T and minus the work. Good? This one clear? Now with the volume, that is held constant, we should have the work equal 0. Then this expression becomes change in internal energy equal NCV delta T. Is it okay? Good until now? Then we are able to find a new expression for the CV, molar specific heat at constant volume. So CV equal, which is the ratio of the change in internal energy to N delta T. Good? And remember once again, we just found that internal energy can be expressed in this form. Here. Chúng ta vừa mới thiết lập cái biểu thức này đây ạ. Đúng không ạ? Bây giờ ta thêm cái delta vào đây ạ. Delta vào đây. Thì ta có cái này. Good. You still follow me until here?
Yes.
Good. Then we should be able to have this expression. Here, this is the molar specific heat at constant volume. Molar specific heat at constant volume for a monatomic gas. Okay. 3/2 times R, and if we replace the value of R, we should be able to have the value for CV. This is the molar specific heat at constant volume of any monatomic gas. Any monatomic gas. So this is CV. How do we consider the CP? Now, okay, here, before going to that part, I give you some example. For example, here, this is for the ideal gas. Here, this is for the real gas. So we see that the two values, here, this is our model of an ideal gas. Okay? We use the kinetic theory of gas to calculate. Here, this is what we measured. So what we see here is that the model, our model, matches very well with the reality, with the measured ones. Good, so we can say that, okay, we can still use the very simple model of the ideal gas to explain the real situations of the gas. Now, we consider the value CV for diatomic gas. Good, diatomic gas. Now, we calculate the CV for the diatomic gas and polyatomic gas. Good. The diatomic gas and the polyatomic gas, can store energy in the form of rotational kinetic energy also. So in quantum theory, they say that when you have starting from two atoms, that atom can have also the rotation, and this is also another form to store energy. Beside the translational kinetic energy, it can have also rotational kinetic energy. It means that it will have more energy for CV and also for CP. Good. And here, when we add a certain amount of energy to a diatomic or polyatomic gas, only a part of it will be transformed to become the translational kinetic energy to increase the temperature. Another part is served for the rotational kinetic energy. Then, if we try to generalize our formula, we should be able to have this one. And this one is true for any ideal gas. It can be monatomic gas, it can be diatomic gas, it can be polyatomic gas. So, I back here again, you see this is for monatomic gas. Okay, this is true for any gas. Is it okay to hear? Please remember very well this expression, because you will see it again and again. This one is true for any ideal gas and any process. change in internal energy equal NCV delta T. Okay? Now, okay, if you noted, then we go to the molar specific heat at constant pressure. We reconsider again our problem, but now we keep our pressure constant. We keep our pressure constant. When we raise the temperature, so only the volume will change. The pressure is held constant. Then the change in the volume will be this part. Okay? Here we want to find an expression of the Cp, the molar specific heat at constant pressure. If we increase the temperature while keeping the pressure unchanged, then the volume of the gas will be changed by an amount of P delta V. You agree? Then the heat, this time, the heat is actually Q and Cp delta T. And is it okay to hear? Q equal and Cp delta T. We write it when we have constant pressure. Okay? When we have a constant volume, Q equal NCV delta T. When constant pressure, Q equal NCP delta T. And we try to relate the molar specific heat Cp and Cv. Remember this one, right? This one is true for any process. This one is true for any process. This one, for constant pressure. Then if we replace the ideal gas, we should calculate the work. So the work will have this expression. You follow me? Then if we replace it into the first law, we did like previously we did it, we should have this expression. Is it okay? We should have this expression. Here, this is true for any process. Here, this is the heat we supply to the gas at constant pressure and Cp delta T. And if we use the ideal gas and the first law we developed, and at the end we will have this expression. Cv equal better this one, Cp equals Cv plus R. So this is the relationship between Cp and Cv. Cp and Cv, a difference in R. Okay? Here, if we look in a whole picture, this is the monatomic gas, and this is the diatomic gas. What we see for a monatomic gas, the heat at constant volume will be used to raise the change in internal energy. Okay, to raise the internal energy, and that change in internal energy will be served for the translation of kinetic of the molecule. and only the translation of kinetic of the molecule. Meanwhile, if we supply the heat at constant volume for the diatomic gas or the polyatomic gas, one part of that energy will be served for the rotation, and one part of that energy will be served for the translation of kinetic energy. Is it okay? Good. Here, this is the value, the expression for the heat at constant pressure. Constant pressure. At constant pressure, the heat supply, one part will be served to do work, and one part will be served to increase the change in internal energy. And after that, the change in internal energy will be served to transform to the translation of kinetic energy, and so on. Here in the diatomic gas, if we supply the heat at constant pressure, one part is to perform the work. For the gas to expand, right? For the gas to expand, we need a certain work. So one part of the heat will be supplied to do work, and another part will be supplied for the rotation and the translation of kinetic energy, and it will have this value. Cho monatomic gas này, thì khi mà chúng ta cung cấp năng lượng cho cái khí của chúng ta ở cái thể tích không đổi ấy, thế thì cái nhiệt lượng này nó sẽ được dùng để làm gì ạ? Nó sẽ làm tăng cái nội năng của khí, và cái nội năng này nó sử dụng chính để cho cái chuyển động thẳng của phân tử, của cái phân tử khí. Thế nhưng mà ở cái điều kiện, đây là ở constant volume nhé, ở điều kiện thể tích không đổi, ở điều kiện áp suất không đổi, thì khi mà nhiệt lượng ta cung cấp cho một cái khí của ta, monatomic gas, thì cái một phần của nó sẽ được sử dụng đầu tiên là để sinh công, để cho nó nở khí ra này. Đây ạ, nó cần phải sinh công ở đây, thì một phần năng lượng nó được sử dụng để sinh công, một phần năng lượng nó mới dùng để tăng cái nội năng lên, tăng nội năng của khí lên. Tuy nhiên ở cái diatomic gas thì nó phức tạp hơn một chút, ở thể tích không đổi thì cái nhiệt lượng mà cung cấp vào nó sẽ phục vụ cho hai việc, cho cái phân tử của ta. Một là có cái năng lượng để chuyển động thẳng, hai là có cái năng lượng để chuyển động quay, thấy không ạ? Và ở constant pressure thì nó cũng làm thêm một cái công việc nữa, đó là sinh ra công để làm sao cho cái khí nó nở ra đó, một cái đoạn là P delta V. Được chưa ạ? Good. So remember once again. This one is the CV for monatomic gas. Good. This one, is the internal energy of any gas. Monatomic gas, diatomic gas, polyatomic gas. Okay? And the change in internal energy can be written S and CV delta T for any gas. This one is the difference between CP and CV. Here, CP and CV. Good. And here, these are some values, if you can remember, of the heat. This one is for the diatomic gas at constant pressure. So the heat supplied to the diatomic gas will have this value. And here, this is the value of the heat supplied to a diatomic gas at constant volume, which is equal to the value of the heat supplied to a monatomic gas at constant pressure. And here, this is the value of the heat supplied to a monatomic gas at constant volume. Good. If you are able to memorize this one, it will be very helpful for you, because we already summarized mostly everything here. Okay? Nếu mà các bạn nhớ được cái biểu đồ này, các bạn sẽ thấy rất dễ này. Ok. Monatomic gas delta E bằng 3/2 L delta T bằng Q này, ở constant volume này. Đó, tương tự này, constant pressure thì ta có cái expression là như thế này này. Đó, với diatomic gas thì cái thằng này heat at constant volume thì bằng cái thằng monatomic gas heat at constant pressure, và heat at constant pressure thì nó cao hơn hẳn một bậc, nó được tính như thế này, được chưa? Here, let's try to wake you up to do some very small exercise. So the amount of heat required to raise the temperature of the unit mass of gas through 1 degree at constant volume is, right? This one, this is the meaning of CV. So CV is actually the amount of heat required to raise the temperature, of the unit mass of gas through 1 degree at constant volume. And which one of the following is the correct relationship? Cp plus Cv equals 0. Cp equals 1 plus R over Cv. So which one? D, right? Yeah, the answer is D here. Continue. The heat capacity, okay, you know the heat capacity depends on whether the heat is added at constant. Here, constant volume or constant temperature or constant pressure or constant volume. Which one is the right way? The heat capacity.
B.
Yeah, question. The answer is B. The heat capacity depends on whether the heat is added at constant pressure or constant volume. Good. Because if we have constant temperature, we do not have the heat capacity, constant pressure or constant volume. Now we consider the helium as an ideal gas. Then what is the Cv for this gas? Yep. Okay. So you know how to calculate it. Is it okay? Then we continue. Yeah, should be a very easy. Now we go into a small exercise for you to practice. Now I have 5 mole of helium. I have 5 mole of helium. It has a temperature of 20 degrees Celsius at constant pressure. Constant pressure. Okay. I'm sorry. So here we have the change in the temperature is 20 degrees Celsius. The change in temperature. So this bubble of helium will go from, for example, this position to go to this position at a change in the temperature of 20 degrees Celsius. And that gas expands. What we want to know first is how much energy is added to the helium as heat during the expansion. So we have to calculate the heat. Then what will be the change in internal energy of the helium? Then how much work is done by the helium? How much work? So we do it together, right? Well, first question, how much energy is added to the helium as heat during the increase and expansion? We know, what do we know? We know the number of mole, right? What do we know? We know the change in temperature. Good? And we know that the pressure is constant. Then we should be able to use the expression of Cp. So Q equal N Cp delta T, right? Then what else? Here, if we develop more, we should be able to have this value, right? The heat supplied to a monatomic gas at constant pressure should be equal to this one. Then for question A, we have this result. Is it okay? This is for the question A. So we use Q equal NCP delta T. And when we develop it, we should be able to have this expression and this result. Good. Now, once we have the heat already, right? We should remember the heat. Here, for the question B, we have to find the change in internal energy. The change in internal energy. So we know that the change in internal energy can always be calculated using this one. Is it okay?
Yes.
Then we should be able to have the change in internal energy. Good. Remember here is CV, not CP, okay? Look at here. The change in internal energy. When we supply the heat, good? Supply the heat. For example, if at constant pressure, only one part of this heat will be used to increase the change in internal energy, and which is equal to this one. Not only all the heat is supplied, all the heat supply is to use to increase this one. No, it's not. One part of it is to do work, to expand the gas. That's why here we have the CV and not CP. Các bạn chú ý phần này nhé. Giống như lúc nãy tôi giải thích đấy ạ. Khi mà ta cung cấp nhiệt lượng cho một cái mol khí của ta ở cái điều kiện áp suất không đổi, thì một phần của cái nhiệt lượng này nó được sử dụng để nó sinh công. Đó, để nó sinh công, để nó thay đổi cái thể tích này. Và chỉ có một cái phần khác nó mới được sử dụng. Đó, nó mới được sử dụng để nó làm thay đổi cái biến thiên nội năng. Và cái phần được sử dụng để thay đổi cái biến thiên nội năng nó là cái này. Được không ạ? Nó là cái phần này. Và cái phần này thì nó được tính bằng cái công thức là này. Được không ạ? NCV delta T. Cho nên là vì sao nhé? Cho nên vì sao các bạn đừng hỏi là tại sao ở đây nó lại không phải ta dùng CP ở đây. Đúng không? Bởi vì không phải là toàn bộ cái năng lượng cung cấp vào ở cái điều kiện áp suất không đổi là nó được sử dụng để nó tăng cái biến thiên nội năng lên, mà chỉ một phần của nó được sử dụng để tăng biến thiên nội năng, và cái phần đó thì nó chính bằng cái NCV delta T. Cái phần còn lại ấy, cái phần R còn lại đó là nó được sử dụng để nó sinh công. Được chưa? Phần này ok chưa? Các bạn chú ý nhé. Biến thiên nội năng thì là nó luôn luôn nó được tính bằng công thức này, nó không phải CP là vì thế. Bởi vì CP nó không được cái sử dụng cái nhiệt lượng cung cấp. Nhiệt lượng cung cấp ở CP ấy, nó sẽ không được sử dụng hết để làm tăng cái biến thiên nội năng. Good. Now for the question C. How much work is done by the helium? We can use the ideal gas to have this expression. And another way, we can use the first law to directly have the result. We can apply both ways. Good? So these kinds of exercises will be very suitable for your exam. You'll be very suitable for your exam. Is it okay? I invite that you take another break of 10 minutes, and after that we will finish the last part. Em nói đi. Nhá, cho bạn nào vẫn còn mơ hồ một phút này. Đó, các bạn chú ý, nếu các bạn nhớ được của tôi cái biểu đồ này thì nó sẽ rất là dễ. Cái sự khác biệt giữa nhiệt lượng cung cấp cho khí ở constant pressure và constant volume nó chính là công. Nó chính là công. Cho nên khi ta hỏi tới cái biến thiên nội năng thì nó chỉ có mỗi cái phần năng lượng này nó được cung cấp cho khí. Đó, cung cấp cho khí. Cái phần còn lại là nó được dùng để sinh công.
Em xem một lần nhé.
Nói quá nên là giọng nó cứ tắt dần thôi em ạ. Các bạn chú ý nhé, cái phần CP và CV này nó rất là quan trọng. Molar specific heat and constant volume. Ta chú ý là CP, CV nhá. Ở thể tích không đổi thì cái nhiệt lượng cần thiết để cung cấp cho cái khí của một mol khí của ta để nó tăng lên 1 độ thì ta có cách tính, đúng không ạ? Thế nhưng mà đấy là ở thể tích không đổi, that's constant volume. Thế ở áp suất không đổi thì nó lại khác. Áp suất không đổi thì nó cần nhiều năng lượng hơn để nó tăng 1 độ, đúng không ạ? Ở áp suất không đổi thì nó cần thêm một cái phần để nó sinh công nữa. Cho nên là vì sao là CP nó cao hơn CV. Cái nhiệt lượng cần thiết để cung cấp cho khí của chúng ta, cho 1 mol khí của chúng ta để tăng cái khí đó lên 1 độ, 1 độ C đó, hoặc là 1 Kelvin. Ở cái điều kiện áp suất không đổi thì nó cao hơn ở cái điều kiện thể tích không đổi. Bởi vì nó cần một cái phần để nó sinh công. Và cái khác nhau của nó chính bằng hằng số khí lý tưởng đó. Nó chính bằng cái R. Nếu các bạn nhớ được cái ý thì rất là dễ. Cái thứ hai nữa là các bạn nhớ là giữa monatomic gas và diatomic gas thì cái diatomic gas nó sẽ có một cái mức năng lượng nó lại cao hơn nữa. Bởi cái vấn đề là sao trả đi? Đây. Bởi cái vấn đề là năng lượng bây giờ nó cung cấp vào để làm tăng cái biến thiên nội năng này thì cái biến thiên nội năng này nó lại có một phần để nó sử dụng cho cái năng lượng quay của cái phân tử. Cho nên vì sao cái biến thiên nội năng của thằng này nó cũng cao hơn thằng này. Nên là cái năng lượng cần để cung cấp để tăng nhiệt độ của cái khí này lên 1 độ nó lại lớn hơn nữa là vì thế. Được chưa? Chú ý nhé, chú ý mấy cái điểm. Vì sao nó có cái mức năng lượng này khác nhau. Và sau đó thì chúng ta đã thiết lập được các cái công thức để chúng ta tính toán, chúng ta ra được các cái giá trị này. Đó. Nhiệt lượng cần cung cấp này thì nó sẽ bằng cái công thức này. Nhiệt lượng cần cung cấp ở các cái điều kiện khác nhau nó sẽ bằng các công thức này. Ok nhé. Now we continue. Phần này hơi khó một tí nhé, cho nên các bạn tập trung. Chúng ta cũng hiểu vì sao ở đây là nó chỉ là CV là vì thế. Được chưa? Now we go to a quite good question. We talk a lot about the specific heat and how do we measure it? How do we measure it? It's another problem. Yeah, how do we measure it? It's another problem. Here, let's say, how do we measure it? How do we measure the C? Yeah. What we have here is a calorimeter. If you have time, I invite you to go to the the laboratory 510 So this is my laboratory. We have exactly the same. This one, exactly the same model. And this model is quite costly. It's around 500 millions. Yeah, cái máy này khoảng 500 triệu. For the purpose of just measuring the specific heat of a substance. So the formula is very easy, right? If we know the heat, the amount of heat supplied to the substance, we know the change in the temperature, we know the mass. We should be able to calculate the specific heat, right? Q equal mc delta T. The mass of the substance, we can measure it using weight, right? The heat supplied to that we can measure it. The change in temperature is even easier, we can measure it. But we still need very expensive equipment to be able to do so. For the purpose of accuracy, that we need a precise result. So for example here, this one we call a Bond calorimeter. We call a Bond calorimeter. Here we have a bomb, very heavy. We will put the sample inside after knowing the mass of that sample. And then we close it. We close it. We will supply oxygen, pure oxygen, under very high pressure. For one reason, what we want to do is to completely burn, the sample inside. So before burning it, we have to put this bomb into a bucket. This bucket will contain a certain amount of water. So the purpose is that when we burn the sample inside, a certain amount of energy will be released. Okay? So we have the Q. That amount of energy, after being released, will be transferred to the wall of this bomb. And once again, to the water inside the bucket. Good. So one part we have Q1 equal M1 C1 delta T. Okay? In another part, we have Q2 equal M2, which is the mass of water, C2, which is the specific heat of water, we know, and the change in internal energy, we should be able to measure using the sensors. So, the only thing we do not know is the C. Is the specific heat. Đúng không ạ? Chúng ta cho hai cái cân bằng nhau thì một bên chúng ta có Q1 từ mẫu thoát ra, chúng ta biết chúng ta phải cân chỉnh mẫu, chúng biết M1 là M của mẫu chúng ta đo được, C của mẫu chúng ta không biết, delta T chúng ta đo được. Cái phần thứ hai, bởi vì nhiệt lượng của mẫu tỏa ra nó sẽ truyền tất cả vào nước. Phần thứ hai, nhiệt lượng của nước, đúng không ạ? Thì cái phần nhiệt lượng tỏa ra đó nó sẽ bằng là M của nước này, C của nước này, ta biết này, và delta T ta đo được. Thì từ cách đó là chúng ta sẽ đo được cái CP của cái vật của ta, của cái chất của ta khi mà ta cho vào. And why we need a very expensive ones? Because we need precision. We need the precision in our measurement. We need a very well isolated system. And you know that it's really hard to create a well isolated system in our open environment like that. This is a little bit of practice that you might do with me during not this year, but maybe next year. because this one is quite expensive. I also cannot welcome 600 people in my lab. But if you follow the second year and your programs has something related to thermodynamics, I think you will have the chance to go to the lab and do this kind of practice. Is it okay? This is a part of practice. We should continue to try to finish in time. Now, we will talk about the degrees of freedom and the relationship between degrees of freedom and moral specific need. What is the degrees of freedom? Ever heard about it? Degree of freedom. Degree of freedom. The degree of freedom. Yeah. So we know that the molecules with more than one atom. So here we mean the diatomic gas, the polyatomic gas, can store energy. Okay? Can store the internal energy in the form, in different forms, not only the translational kinetic energy. It can store internal energy also in the form of rotational energy. For example, the oxygen, it can rotate in this direction, or it can also rotate in this direction. So this is for a diatomic gas. For helium, we do not consider the rotational kinetic energy. For diatomic gas, we consider it. Here it has two ways, right? Two ways for our diatomic gas to rotate. One way, this is one way. So the y-axis, this is one way. It rotates. The x-axis. For the CH4, it's even harder. For the CH4, so it can have translational kinetic energy, it can have rotational kinetic energy in a lot of forms. Then, if we consider the three models here, monatomic gas, diatomic gas, and the CH4, we see that all the three can have translational motions. So this one can move left, right. So this is one way, okay? Left, right. It can move up, down. Okay? And rotational motions. Okay? Rotational motion. But the diatomic and polyatomic molecules can also have, for example, oscillatory motions. Nó dao động tại chỗ đây ạ. Oscillatory motions. Okay? So we call the degrees of freedom the ways. The ways our gas molecule can have to store energy. So, by this definition, we know that the polyatomic gas will have a degree of freedom that is greater than the diatomic gas and greater than the polyatomic gas. So the ways, the number of ways our gas molecules can store energy. Okay, we call it the zodiac. We call it the degree of freedom. Good. Zodiac. Bạn nào còn ngủ zodiac? Tự nhiên gần 10 giờ rồi mà lại ngủ hết thế này. Vào lớp rồi. Bạn nào đánh thức tôi cái bạn kia đi. Nhớ chưa ạ? Ăn sáng chưa ạ? Good. Now we try to establish the relationship between the degrees of freedom and the molar specific needs, what we just seen. Okay? What we just seen. We try to relate the degree of freedom. So the ways. Các bạn tập trung vào thôi. The ways our gas molecule can store energy and the molar specific heat. So we start. Firstly, we consider the theorem of the equipartition of energy. So J. Maxwell, he said that every kind of molecule has a certain number of degrees of freedom. Okay? Which are independent ways in which the molecule can store energy. So, this is the definition of the degree of freedom that I just explained. Then, each such degree of freedom has associated with it, on average, an energy of half kT per molecule, or half RT per mole. Is it okay? So this is the equipartition of energy, the theorem of the equipartition of energy. Every kind of molecule has a certain number of degree of freedom, and each such degree of freedom has associated with it an energy of half kT per molecule, on average, or half RT per mole on average. Is it okay? So we try to establish the associated energy per molecule for a monatomic gas, because now we want to relate the degrees of freedom and the molar specific heats. Then, for our monatomic gas, this one, we have the model of helium. This will have the 3 degrees of translational freedom and no rotational freedom. Okay? So it means that our helium here can move on the x-axis, on the x-axis, y-axis, and z-axis. Okay? It can move in 3 directions. So it will have 3 degrees of freedom. And it has no rotational freedom. Good. Then the energy, the associated energy per molecule is this one. You agree? For a diatomic gas, now for a diatomic gas, one diatomic gas like this one will have 3 degrees of translational freedom. right? Plus 2 degrees of rotational freedom, like this and like this. Then it will have an associated energy of 5 times of this one per molecule. Is it okay? Is it okay? If now we replace our general formula of the internal energy, this one, okay, with this one is for the monatomic gas, okay, 3 degrees of freedom. We try to generalize. We replace not only 3 here, because 3 here corresponds only to the monatomic gas. I will replace this formula with the degrees of freedom, yeah, for it to be true for any gas, for monatomic gas, for diatomic gas. Then we should be able to have this expression for the CV. Okay, we should have this expression for the CV. You follow me until here? Yes? Good? So here it says that the CV, so the molar specific heat, the heat needed to rise 1 mole of a substance by 1 degree Celsius depends on the degree of freedom. So the more degrees of freedom the gas has, the more energy is needed to raise that gas to by 1 degree Celsius. Cái khí mà nó càng có nhiều bậc tự do, có nghĩa là nó càng có nhiều cách để nó dự trữ năng lượng cho nó ấy. Đấy, càng có nhiều nó có chuyển động năng, nó có năng lượng dự trữ khi mà nó quay. Thế thì nó càng cần nhiều năng lượng, đúng không ạ? Để cho tăng nó lên 1 nhiệt độ thì nó càng cần nhiều năng lượng hơn. Và cái này thì nó có mối liên hệ trực tiếp với nhau. So it has a direct relationship between the degree of freedom of a gas and the specific heats. Dậy, gọi rồi, đi rửa mặt đi. Khổ quá. Okay, is it clear to you here? Here, if we are back to this table, and if we look at this table, what can we say when we compare this one and this one? Yeah, what can we say? Here we have the monatomic gas, the diatomic gas, we have polyatomic gas, we have the number of CV for an ideal gas, our model, okay? And for the real gas, here we have the degree of freedom measured for our monatomic gas, for the diatomic gas, and for the polyatomic gas. Here we take the example of CH4. Of course, we can have different polyatomic gas with different degrees of freedom. Yeah, not only 6 here because we use the CH4, then it has 6 degrees of freedom. But what can we see? This one is the predicted molar specific heat. predicted molar specific heat. If we compare it, we see that the prediction, okay, because we are using our model of kinetic theory of gases. We are using our model of ideal gas to predict things. Then, what we see here is that the prediction agrees with the experiment. This one is the experiment. This one is the experiment. Agrees with the experiments for monatomic gas and diatomic gas. Right? For monatomic gas, it has 3 degrees of freedom, and Cv is this value. Okay, and it agrees with the experiment. For diatomic gas also, it has 5 degrees of freedom, and if we calculate it, the predicted molar specific heat will be this one, and it also agrees with the experiments. But for, you see here, for the polyatomic gas such as CH4, the predicted molar specific heat here is only 3R. 3R's mean this value. And for the real gases, it has this value. Okay? So then, what we see is that this one is still too low for polyatomic gas. So, the kinetic theory of gases can predict pretty well for monatomic gas and diatomic gas. But it has a limitation, you see here. It has a limitation when calculating the polyatomic gas. You see? Yeah. Good. So any question until here? Is it too difficult to follow? A little bit. Anyway, we need some more practice. That's why even for the tutorials, we place 2 sessions of tutorials for this part. So through exercises, you will understand a little bit better just by looking at the slide. Now, yeah, that's why each time I have to stop and then I give you some small questions to see if you already understand correctly. What is the value of ratio between Cp and Cv for a gas of monatomic molecules? The value of ratio between Cp and Cv for a monatomic gas. So monatomic gas, Cv equal this one, Cp equal this one. Then Cp plus Cv is actually this ratio, if I calculate correctly, right? So this is the ratio between Cp and Cv. Then, what is the value of molar specific heat of a diatomic gas at constant pressure? For diatomic gas, to be sure that you still follow the slides. Bằng bao nhiêu ạ? So, the Cv for a diatomic gas can be calculated using this one. Cp is actually the difference of R, right? Then we should be able to have this expression. Is it okay? Move on. Now we consider another problem of the adiabatic expansion of an ideal gas. Adiabatic expansion of an ideal gas. Giãn nở gì ạ? Giãn nở gì ạ? Vâng, đoạn nhiệt ạ, của khí lý tưởng ạ. Giãn nở đoạn nhiệt. I go back to my example. You should still remember this example, right? I have my cylinder here. Inside I have a gas. So the gas inside is very well insulated. Here I have the electrode. Okay? And now I slowly remove the electrode to allow the expansion to happen, but without any heat transfer. So I am trying to do an adiabatic expansion for my ideal gas. Then if I consider a very small change in the volume, very small change in the volume, I can consider that the pressure of my system is constant. In this way, the first law can be written in this form. Can be written in this form of the differential. So differential internal energy equal this form. Okay? Equal this form. Now, because we say that there's no heat in an adiabatic expansion. Okay? In the adiabatic expansion. This one equals 0. You agree with me? And the change in internal energy can be calculated by the expression NCV delta T, right? The differential also. So we substitute the heat, okay, and the internal energy. This one we saw in previous slides. Then we will have this expression. So here we replace internal energy. Here we replace the heat. Okay, then we should have this expression. Please write it down. So we continue. Please write it down. Yeah, do not just look at my slide. Write it down. Then we can continue. So we continue. Okay. Now we use the ideal gas. We use the ideal gas. From here, we use the ideal gas PV equal nRT. We replace this one. This one is from the ideal gas. We take the differential of the product dV, right? And this one PV should be equal nRT. So that's why I write like this. And what you see here, the differential of PV is actually, this is mathematics, V dP plus P dV. Okay? And this one equal nR dt. Am I right? Then we know that R is the difference between Cp and Cv. R is the difference between Cp and Cv. Then we can rewrite the expression and this becomes this one. Okay? If you follow me. Then we continue to develop our expression. Continue to develop our expression to have this one. to have this one. You can write it down and then you verify it at home. Good? We have this one. Because our purpose is to have an expression. Yeah. Now, okay. Here we have the ratio between CP and CV. We have a ratio between CP and CV. I call it gamma. Good. To simplify things, I call it gamma. And if I integrate this one, I integrate this one and this one. Okay? If I take the integral, then I should have this formula. Mathematically, I have it. Is it okay? If I solve it, you agree with me? Here, I solve it mathematically. I should be able to have this expression. Các bạn còn nhớ toán học không ạ? Đúng không ạ? And finally, once I have this one, yeah. You follow me? Is it okay until here? Then we solve the expression to become this one. Is it okay? And from this one, we can say that we have this one become constant. Ông không xem hentai à? Giỏi lắm nhỉ? Tập trung đi. Okay, so this one is actually the exponential of Ln here. It's actually this one. So we can say PV gamma is a constant. Is it okay? Here we can apply, we can apply the ideal gas law. And we continue to develop. And at the end we should have this expression. And this expression can be applied. For the adiabatic expansion of an ideal gas. This is a little bit hard. Please follow me. Okay, this expression can be applied for the adiabatic expansion of an ideal gas. Is it okay? Good. However, this cannot be applied for an adiabatic free expansion, because for an adiabatic free expansion we just have the Ti equal Tf. So there's no change in temperature. Then the above equations cannot be applied. So this is an important expression that we can apply for the adiabatic expansion. Is it okay? You can remember this one also, PV gamma equal constant. Or we can remember this one also. We have two formulas to remember for an adiabatic expansion of an ideal gas. We can also go to the four special processes. that an ideal gas can undergo 4 special cases of an ideal gas. This is the last slide of today, so we focus. Here we have the isobaric process. Remember isobaric process. What do we have? This one, the first law, we always have. This one, the change in internal energy, we always have it. I already explained why, right? Now, for the first special case, isobaric, what do we have? Q equal NCP delta T. Good? You know why? In this time, the work is P delta V. Okay? P delta V. Isobaric. For isothermal process, what do we have? Isothermal process. This one we learned already. The work equal the heat equal this one, and the change in internal energy equals 0, because we know already that this one depends only on the temperature, so then the change in internal energy should be equal to 0 for that reason. For adiabatic process, we just established we have 2 constants. So this one and this one is a constant. This one is a constant, this one is a constant, we trust it. Okay? And the heat is 0. The work, according to the first law, is minus the change in internal energy. And for the isochoric, the constant is the volume of cause. Here, the heat will be equal to the change in internal energy and equal to NCV delta T, and the work equals 0. Here, this is the combination of what you have learned during the first part, the first law of thermodynamics, and this part, the part of ideal gas law. Okay? So, also please remember very well this table. It will be very helpful for you. Here we already summarize. Good. For special cases. Here I have some exercise. We can do it next time. I stop here. This part is a little bit hard because you see there are a lot of new definitions. There are a lot of new knowledge for you. Very new knowledge. You haven't seen it during the high school. Am I right? But I hope that, okay, you reread the slide, you rewrite all the formulas, and during the tutorial classes, we are going to do some exercises together. You will remember very well, and then at that time, I can explain more in detail. So I hope you enjoy today, and thank you so much. See you next week. Chương này hơi khó một tí, các bạn cố gắng các bạn về các bạn đọc lại slide, các bạn viết lại để các bạn nhớ nhé. Nó có khá nhiều các cái công thức để các bạn phải nhớ. Chữ khó một tí. Cái phần này thì sẽ có trong kiểm tra cuối kỳ chứ không có trong giữa kỳ. Nhưng mà nó khá là khó. Thực sự đó là cái phần khó nhất của thermodynamics. Nên là các bạn chú ý follow rồi. Cảm ơn các bạn nhiều.